Assalamu alaikum everyone. Welcome to the 15th lecture of our numerical methods course, and today's topic is Runge-Kutta second order and Runge-Kutta fourth order methods. Okay, so the plan for today is to understand the idea behind both of these methods. We'll try to derive the formula for the Runge-Kutta second order method, and we'll see what three different approaches there are in order to come up with the formula. Okay, and we'll try to compare and contrast the results obtained using each of these three approaches, and then we'll do the same set of things for the Runge-Kutta fourth order method as well. Okay, in the case of the Runge-Kutta fourth order method, we have two different approaches again. Fine. Okay, so what are these Runge-Kutta methods? So these are basically yet another set of numerical techniques to solve first order ODEs. Okay, so these numerical methods were invented by the German mathematicians Carl Runge and Wilhelm Kutta, and these methods are basically named after them, the inventors. And for the rest of this lecture, for obvious reasons, I'll try to pseudonymize the names of these methods and call them RK2 and RK4 methods respectively. Okay, fine. So the RK2 method is just like the Euler's method. The RK2 method is also a numerical technique, and we only can solve first order ODEs using this method. And in order to facilitate the solution, in order to come up with the solution, we at first our first order of things is to express the given ordinary differential equation in this format over here. Okay, where ddx of y equals to f of xy, where f of xy is of course a bivariate function, which means the slope that I'm expressing is being expressed as a bivariate function, and we also have an initial condition. Okay, so for a particular abscissa x naught, we know the corresponding value of the dependent variable y. Okay, so this of course implies that x is our independent variable which we can change at will, and according to that change the value of y will change as well. So the value of the dependent variable y at a particular point x naught is given as y naught. Okay, that's our initial condition. So from our previous lecture, we have already seen given a first order ODE how we can express it into this template over here, right? So we have to do the same first step in the case of RK2 method as well, which means we have to fit our whatever first order differential equation that we have, we have to fit it in this template over here. Okay, fine. So now let's derive the formula for the method. Okay, and of course, just like the Euler's method, we will try to invoke the Taylor series and try to come up with the formula. Okay, so instead of showing the derivation from this slide, let's go to our bamboo paper and see how the derivation, how the formula manifests. Okay, so what do we have? We have expressed our slope, say ddx of y, we call it dy dx, as a bivariate function, right? F of x comma y, and we have our initial condition, which is what? Y of x naught equals y naught, right? So this is our initial condition. Now, if you recall, we wrote our Taylor series in a different format, right? In our last lecture, so we'll directly write that format. So our Taylor series was something like this. So the value of the dependent variable y at the I plus 1 step, or after the I plus 1 step, is what? The value of the dependent variable y at the ith step plus the first order derivative of y with respect to x at the point xi comma yi. Then we have h, where h is of course the step size, and by h we mean what? H is equals to the value of the abscissa at the I plus 1 step, or after the I plus 1 step, minus the value of the abscissa, or the x value at the after the step of after the ith step. Okay, fine. This is basically our step size, we call it, or the magnitude by which we are progressing from the left to the right, right? Fine. So the third term is something like this: d square, second derivative, right? So let's write it: d square y divided by dx square at the point xi comma yi point xi comma yi times 1 by 2 factorial h square, right? Fine. And the fourth term we have what? Third order derivative, right? So we have d cube y by dx cube at the point xi comma yi times 1 by 3 factorial h cube. And of course, I am not writing the rest of the terms. The same pattern will keep maintaining itself. Okay, fine. So if you look closely, we can see that if you take the first two terms of the Taylor series, which means by first two term I mean these two terms, we end up with what? The formula for the Euler's method, right? So when we take yi plus 1 equals y sub I plus ddx of y at the point xi comma yi times h, we basically end up with the formula that we have derived for the Euler's method in our last class, right? So that's why sometimes the Euler's method of solving the first order ODEs is also known as what? The Runge-Kutta first order method. Okay, so you can also dub it as RK1. So that's the same thing. So why RK? Why first order? Because we are taking the second term, right? And the second term has a first order derivative associated with it, right? Fine. So to write it more clearly, let me write the bivariate function. Let me replace the derivatives with the bivariate function as well. So it will be more clear. It will be clearer to you. Okay. So you can write this thing as what? Y sub I plus 1 equals y sub I. You can replace ddx of y at the point xi comma yi with what? The bivariate function, the value of the functional value of the bivariate function at the point xi comma yi, right? So let's do that. If xi comma yi times h plus we have what? So since this is the second derivative, which means we are differentiating the bivariate function once. So we have this f prime xi times 1, we have this 1 by 2 factorial h square plus, again we'll differentiate two times, which means the second order derivative of the bivariate function, which is x sub I f double prime x sub I comma y sub I times 1 by 3 factorial times h cube, right? So this thing, this term becomes this, and the rest of the terms will be, let's mark it as ellipsis. Okay, fine. So now what can we do in order to show the formula for the Euler's method? We take the first two terms of the Taylor series, right? So this thing is Euler's method, right? Okay, so it can also be, you can also call it as Runge-Kutta first order method, okay, or RK1 method. Fine. So now how do we come up with the formula for the, say, for the, what do you call it, the RK2 method? So what we'll do is we'll take the first three terms of the uh, Taylor series, okay, which means we'll take y sub I. We'll also take the second term f of xi comma yi times h, and the third term f prime xi yi times 1 by 2 factorial times h square, okay. Fine. So if you take these three terms, the first three terms of the Taylor series, what you end up with is the formula for the RK2 method. Okay. So one obvious pitfall or problem here is that you can clearly notice here, which is we need to calculate the value of f prime of xi and yi, the value of the first derivative of the bivariate function, which is f prime at the point x sub I and y sub I, right? So this thing has to be what? This has to be computed symbolically, right? By symbolically we mean that, okay, what's the differentiation of a bivariate function. So if you recall, if you have a particular, say, if you have a particular bivariate function f of x y, and we know that y is a function of x, which means y is dependent on x. Okay, so this bivariate function over here is not does not constitute two independent variables. Okay, so one of them is an independent variable, which is x, and another variable y is dependent on x, which means it's a dependent variable. Okay, but both of these variables dictate the nature of the bivariate function, which is why it's called bivariate. Okay, which means it has two tweakable parameters or two variables, right? Fine. So if we have a bivariate function where where one of the say call it parameter or call it a variable is a function of another of its variable, we say what the f prime x comma y is something like what you need to perform the chain rule, right, of differentiation, which is something like what partial derivative of f of x comma y with respect to x plus the partial derivative of this bivariate function with respect to y times the differentiation of y with respect to x, right? So this is basically the chain rule that we have learned back in our differential calculus course, right? We have also learned it in our HSC higher maths, higher maths subject, right? Fine. So what happens here is that if you want to calculate this value symbolically, which means using a set of rules, the implementation or the code implementation gradually starts to get out of hand, right? We have basically discussed this thing. We have basically discussed these things back in our earlier lectures, right? Which is that in order to in order to come up with solutions analytically for some problems, it starts to become intractable. Okay, which means for computers, it starts to become infeasible to come up with these calculations, maintaining a reasonable computational overhead. Okay, so what we can do is we can approximate the value of f prime xy. Okay, instead of symbolically coming up with the accurate result. So that's the contribution of Runge and Kutta. Okay, so in their methods, what they did was they leveraged the numerical approximations of f prime of the first derivative of this bivariate function without the loss of too much accuracy. Okay, so whatever value that they approximated was nearly equal to the exact value. So we'll discuss how they came up with the numerical approximations to these of this first order derivation of this bivariate function. Okay, so let's head back to our slide and see what they did. Okay, so we are back. Okay, so this slide basically portrays the same thing that I have tried to impart in our bamboo paper just a while ago. Fine. So let's move on. So in how did Runge and Kutta come up with the approximation of this the penalty of the last term and the penultimate term of this portion of the Taylor series that they considered, right? The first three terms that they considered for the Taylor series, how did they approximate the summation of the second term and the third term, okay, in their formula? So let's see how did they do it. So what they did was they came up with the weighted sum of two slope values at two different points. Okay, so the first slope value is k sub 1 and the second slope value is k sub 2. Now if you are not understanding what k1 and k2 are meaning, we will try to visualize it in a bit. So hold your breath. Okay, uh, ju- for now I'll just discuss the theory and I'll demonstrate the say graphical visualization in our bamboo paper in a bit. Okay, so wait a bit. Fine. So what they did was, okay, they kept a y sub I plus 1 as y sub I plus 1. They kept y sub I as y sub I, and for the final two terms what they did was they approximated this whole sum over here, which was k1 k1 plus k2 k2 times h. Now if you look at this formula over here, this is kind of the concise and most compact form of the RK2 method formula. So you can draw a resemblance between this formula and the straight line equation, right? So if you say, okay, y is equals to mx plus c, where of course m is the weighted sum of the two slope values that we are considering. So a1 k1 plus a2 k2 is a weighted sum of two slope values. Okay. So what are these k1 and k2? We'll come to that in a bit. For now, just let's try to understand the structure of the formula. Okay, so since we are multiplying a1 with k1 and a2 with k2, obviously we can imply that a1 and a2 are the weight values, right? So how much importance we are giving to the first slope value and how much importance we are giving to the second slope value. We add them, we multiply those importance metrics and sum them up with the slope values. We multiply them with the slope values and sum them up, and whatever we get is a slope value that we'll use in our final or compact version of the formula. Okay. Now, why is h being dubbed as x? Because h is what the difference between step size, right? Difference between adjacent x values, right? So the difference between x sub I and x sub I plus one, right? So basically the difference between consecutive abscissa values, right? Right. And why is y sub I can be, why can we call it the y-intercept? Because it will be clear to you once we draw the picture, the graphical picture. But what happens is that in our previous iteration y sub I, we ended up at y sub I, right? Uh, in our previous iteration I, we ended up at y sub I. So for the next, or for the estimation of the next y I plus 1, we start from y sub I, right? So you can basically consider it to be our y-intercept of the very line that we are coming up with, whose slope we say that is a approximation of the I plus approximation of the slope at the I plus one iteration. Okay, so it still may be a bit abstract right now. It will be clear in a bit, inshallah. Okay, so what are these slope values, the k1 and k2 slope values? Okay, so Mr. R and Mr. K said that okay, why we'll try to calculate the first slope value at the point f x y, at the point x y and y I. Okay, which means the functional value, the bivariate functions functional value at that particular point, which obviously gives us the slope, right? Because we have said that okay, dy dx is our f of x comma y, right? So the slope at the point x sub I and y sub I is our first slope value, okay, or k sub 1. And what's our second slope value? It's the slope value at a particular intermediary point between x sub I and x sub I plus 1. Okay, so when we go from the point x sub I to the point x sub I plus 1, we say that we go ahead by one step, right? Or we progress by the magnitude of the step size, right? So at some point between that, between the starting point of the step and the ending point of that step, we take another slope value k2. Okay, so why intermediary? Because you can see that a portion of the h value is being added with the xi value, right? And at that particular x value, we are taking an approximation of the dependent variable y. Okay, so they have used the uh, new coefficients p sub I and q sub 1, p sub 1 and q sub 1 1 in this case. You can also write it as p and q if you want. Okay, in my opinion these subscripts are not important. Okay, they can be removed if needed. So these two slope values, one at the point x sub I and y sub I, and another at a particular intermediary point between the starting point of the step and the ending point of the step. If we take these two slope values and take the weighted sum of them, so whatever the weights are is entirely up to us. Okay, how much importance we want to give to a particular slope is entirely up to us. So if we take that weighted sum and multiply it with h and add it with y sub I, whatever approximation of the dependent variable we get, we say that that approximation is the approximation of the dependent variable at the I plus 1 step. Okay, fine. So as we have already discussed in our last lecture, the main goal of these first order differential equation solving numerical approaches is coming up with particular dependent variable values or dependent y values at particular discrete points, right? Instead of coming up with a continuous equation. So okay, so now that we know what the structure of the formula for the RK2 method is our goal is to find out these unknowns, right? These coefficients, these weights a1, a2, and these say these coefficients p sub 1 and q sub 1 1, right? So what we can do is, okay, how do we find these four unknowns? So if you take the equation, let's call it this equation 5. So okay, let's go back to our bamboo paper and try to put things more into perspective. Okay. Okay, so let's go to the next page. We change the color a bit. Okay, so what did we do for the RK2 method? We considered the first three terms of the Taylor series, right? So y sub I plus 1 equals yi plus, say what, it was f of x I sub y, x sub I comma y sub I, the functional value at that point, times h, plus we have what, the first derivative x at the point xi yi, we have h square by 2 factorial, right? That this is the first three terms that we are considering. These are the first three terms that we are considering for the RK2 method. Okay, so Runge put us said that, okay, instead of calculating the f prime xi yi symbolically, what we'll do is we'll say that this part can be approximated as something like this. Okay, so you can say, let me write the whole equation, the full fine compact form of the equation, which is x sub y plus 1 equals y sub I plus a1 k1. So this is one of the slope values multiplied by its weight, plus a2 k2. Okay, and that's the second slope value multiplied by its corresponding weight, times h. Okay, so we can say, okay, this is something like uh, y equals c plus mx. Okay, so this thing is, we can call the new value of the dependent variable y sub I plus 1, which is the value of the variable y at the I plus 1 step. We can say it has the as the y value of the straight line that we are coming with. This is the y-intercept. This whole thing is the slope. So this weighted sum of the slope values, we can consider it the slope of the new line, and this step size is basically the x value. Okay, fine. So what Runge and Kutta did was they approximated the last two terms of the Taylor series, of the three terms that we're considering from the Taylor series. They've approximated it as something like this. Okay, so a1 k1 plus a2 k2 times h. So what did we say back in our lecture slide? We said that, okay, instead of the value of the slope k1 is the functional value of the bivariate function at the point x sub I comma y sub I, right? And what is k2? K2 was the functional value of the bivariate function at a particular intermediary point, right? It was something like, what if I recall correctly, it was something like x sub I plus ph. So I'm omitting out the subscript because I don't think they're needed. Times ph, was it? Yes. And y sub I plus q times k1h. So if you see that this slope value k1 is being reused in order to find the value of k2, right? So k2 is dependent on k1. Fine. So these two are my slope values. Okay. So what we can do is, in order to come up with the equations that I can use to find the values of the unknown coefficients, which are a1, a2. What are the unknown coefficients over here? Let's try to mark them. We don't know what a1 is, we don't know what a2 is, we do not know what p is, and we do not know what q is. Okay, so what we can say is that, okay, since we have these two equations that are basically the same thing, we'll try to uh, express them in such a manner which will help us equate the coefficients of these two expressions. Okay, so if you recall, what does equating the coefficients mean? If we express two separate equations in similar manner and try to say, okay, the coefficients of these terms are equal to the coefficients of the same terms that appear in the second version of the equation, we try to equate them, right? So what happens is that if you try to express these two terms in a similar manner, it becomes a very laborious and what very lengthy task. Okay, so I have provided you the lecture note along with this recording. So if you want to see how to equate the coefficients of these two equations, you can look at the appendix part of the lecture note. At the very end of the lecture note, you'll see a section called Appendix A. Okay, you can go through that appendix and see the actual proof or the derivation of the uh, let's not call it derivation, let's call it the proof of the coefficient of the equating the coefficients. Okay, so if you equate the coefficients of these two equations, what we'll come up with is something like this: a1 plus a2 equals 1, a2b equals half, a2q equals half. Okay, so how do you come up with these three equations? That's beyond the scope of your syllabus. So you don't need to study that for the exam. But for the sake of completion, you can, for the sake of your understanding, or in order to satisfy your curiosity, let's say, you can go through the appendix part of the lecture note and go through the lengthy proof if you want. Okay, but it will not come in your exam. That's for sure. Fine. So what you can see is that, okay, we have what? We have four unknowns, right? We have four unknowns, one, two, three, sorry, one, two, three, and four, right? But for these four unknowns, we are having what? We are having three equations, right? So how do we solve three equations and come up with four unknowns? We can't, right? That's impossible. So we have to uh, have a presumptive notion, or we have to assume one of the values or one of the unknown values. Okay, so what conventionally is done is that the mathematicians, they assume the value of a sub 2. Okay, so they assume or preemptively consider a particular weight for the value of the for the slope value k2. Okay, so the value of a2 is considered as a hyperparameter. Okay, that can be set before running the experiment or before initiating the whole algorithm. Okay, so what happens is that, okay, there are three different schools of thought, or three different approaches of considering or assuming the value of a2. Okay, so we have three equations and four unknowns, so we need to assume one of the unknown values. So we conventionally assume a2. Okay, so the value of a2 is considered what? There are three approaches. Okay, we'll try to outline them. Use a different color. Okay, so we consider the value of a2 to be half, and this approach is called Hwan's method. Okay, this Hwan guy is also another German mathematician, and he came up with this approach. Okay, when we consider the value of a2 to be 1, we call it the midpoint method. You'll be able to see in a bit why it's called the midpoint method. It will be very clear to you. Fine. And the third approach is the considering the value of a2 to be 2 by 3. Okay, so when we do that, we call it the Ralston's method. Okay, so another mathematician called named Ralston, he came up with this value of a2. Okay, fine. So each of these approaches work well for different scenarios. There is no say set in stone best approach. Okay, so you can, for one particular unknown function, let's say the Heinz method will work better for another one midpoint. The midpoint method will work better, and in another one, let's say the Ralston's method will work better. Okay, we'll compare these three approaches for a particular example in a bit, but for now, just understand that there are three approaches of assuming the value of A2. In Heinz approach, we consider it to be half. In the midpoint method, we consider it to be one, and in the Ralston's method, we consider it to be 2/3. Okay, fine. So now that we have one unknown variable already uh, presumed or assumed, we can solve these three equations and come up with the rest of the three unknown quantities, unknown coefficients, right? Which are A1, P, and Q, right? And if we come up with them, we can basically plug them into this formula right here and come up with our corresponding approximations for the RK2 method. Okay, fine. So let's consider the case of the Heinz method and see what the graphical representation looks like. Okay, so a while ago I said that I'll show you the graphical representation. Now let's look at that. Okay, then everything will be clear to you. Fine. Let's go to the next page. Okay, so let me write down the equation that we wrote in our last page for better clarity. So equals what? A1 plus A2 equals 1. This was one of the equations. Then we have A2 times P equals half. This was another one of the equations. Then we have A sub 2 times Q equals to half. This was the last equation, right? These three were our equations, and we said that okay, now we are going to talk about the When's. Let's spell it clear. Let me spell it correctly. We will try to discuss the When's method, right? So in the When's method, we considered the value of A2 to be. Let me use a different color. So A2 is what? Half, right? The value of A2 is half for the Heinz method. Okay, now that we have assumed the value of A2 to be half according to the Heinz method, we can say okay, the value of A1 is what? 1 minus A by 2, right? And 1 minus A by 2 is of course half because the value of A2 is half. So we say that okay, the value of A1 is half, right? Because 1 minus half is half. Okay, so we are also seeing that in our second equation we have A2 times P is equals to half, right? Which means the value of A2 we have already considered to be half multiplied by some quantity is also giving me a value of half. We know it will only be possible if the value of P is half, right? So we can say that okay, the value of P is sorry, not half, 1, right? So when half times 1 is half, right? So when the value of A2 which is half is multiplied by P which is 1, we get the product half. Fine. In the case of the third equation, which is A sub 2 times Q equals half, we can say the same thing, right? Since we know the value of A2 to be half, we can say that the value of Q is 1 as well, right? So the value of Q is 1. Okay, so now that we know the values of all four of our unknown coefficients, let's see what the graphical representation looks like. Okay, so let me write down the equations again here for better clarity. So what did we write? Wrote that okay, our yi plus 1 will be yi plus a weighted sum of the slope values at two particular points, right? So our weights are here half and half. So we are giving them equal priority, right? We're giving them equal weights. So half times the slope value or the first slope value or the K1 value plus half times the second slope value, right? Or the K2 value times h, okay, where h is the step size of course. And if you recall, our k1 was the functional value of the bivariate function at the point xi comma yi, and the k2 was what? The slope value at the point at another intermediary point, right? So since now we know the value of p and q, we can plug them in, right? So we saw that our value of k2 was something like this, right? F of xi plus ph comma yi plus q times k1 times h, right? So since our p and q values are both 1, we can basically write it as something like xi plus h comma yi plus k1 times h, right? So let's do that. So our k2 is something like what, x sub I plus h, which is basically x sub I plus 1, same thing because we are progressing by a step size of 1, or h, or magnitude of h, fine. And we have the approximation of the y value at that particular point, which is y sub I plus k1 times h, okay, where k1 is of course this one. This thing is being used over here as well, fine. So let me write the bracket a bit more concisely. Fine. So these two are our slope values. Okay. So let's take a graph over here. Let us draw the Cartesian axis. Okay. So these are our x values, of course, and these are our dependent variable y values. Okay. Fine. So let's say our unknown curve looks something like this. So of course we don't know what the curve looks like. For the sake of illustration, I'm drawing it. Okay, so let's say it looks something like this. Okay, fine. So for a value at a particular xi, so this is the value of x at the after the ith iteration. We say that okay, uh, if we project it upwards, so at this point we find the value of y sub I, right? Or at that point we say that it's the uh, value of the independent variable at the point x sub I, or when the value of the independent variable is x sub I, this is the value of the dependent variable, right? Fine. So since we know the slope at this point is something like this, right? uh, let's call it like this. Okay, let's say something like this. Okay, so this is perfect. Fine. So this, let's call it the slope at the point x sub I and y sub. So this, of course, is what, x sub I comma y sub I, right? This point over here. So at this point, the particular slope is, of course, k1, right? Because the slope at the point x sub I comma y sub I is the functional value of the bivariate function at that point, at that particular point, right? Which of course we said that this bivariate function denotes or dictates the behavior of the slope, right? So k1 will obviously be this thing over here, the bivariate function's functional value at the point x sub I and y sub I, right? Fine. So this is our K1, the first slope that we are considering. Okay, fine. So our target is what? Our target is to progress by a single step, right? So let's say this is our x I plus 1. Okay. So of course the distance between xi and xi plus 1 is h, right? This whole thing is, so xi plus 1 is one step size ahead of 8x sub I, right? Fine. So the distance will be h, fine. So now what we will do? We will see that, okay, at the value xi plus 1, this is of course for applicable for the Horn's method only. We say that, okay, for the value of the independent variable at x sub I plus h. So x sub I plus h is of course over here, x sub I, and we progress by yet another step. We go to x sub I plus 1, right? So at that particular point, we'll assume a value, or we will approximate a corresponding dependent variable value. Okay. So for the dependent variable, we call it what? Y sub I plus k1 times h. Okay. So we say that, okay, at this particular value, let me project it upwards. So the point at which this straight line meets the projection, we say that at this point we are considering the value of the approximation of the dependent variable. Okay, so this value over here, let me write it. This is x I plus h. This coordinate over here is x I plus h comma what, y I plus k1 times h, right? because we can consider this ordinate part as something like what, as straight lines, as the solution of a straight line, right? Because we have the y-intercept y sub I. So if we consider this part to be the y-axis, if we consider, say, this part to be the y-axis, this thing is our y-intercept, right? So this will of course be the origin, and this whole thing will be our y-intercept, right? So this thing is y sub I, obviously. Write it a bit more clearly. So this thing will be considered the origin, and this whole part over here will be considered the y-intercept, right? So if we draw this partial straight line over here, and we know that the slope of this straight line is k sub 1, right? And we know the value of x to be h, right? So we are progressing along the x-axis by h units, right? So of course this value, this coordinate over here will be y sub I plus the ordinate of this coordinate over here will be y sub I plus k1 times h, okay? And we know the axis of this coordinate will be, of course, xi plus h, right? Because we are progressing by one more step. Fine. So our second slope value will be the slope value at this particular point, okay? So at this particular point, we are going to find out the slope value. Let me denote it using a different color. Let's say something like this. So at this point, let's say the slope will look something like this. So what's the slope? The slope is a function of the bivariate functions, functional value at this particular point. So let's say it will look something like this. So I'm very bad at drawing straight lines using my mouse. So roughly it will look something like this. Okay, fine. So this thing over here, this is our K2, which is what? F of xi. So there is not enough space to write it. So I'll forego writing it. So of course you can see the value of K2 over here, right? So this thing. Fine. So we know our initial first slope value k1, which is the slope at this point. We also know the value of our slope at the second point, which is at this point over here. If we have this, so the slopes are basically represented by the purple part. The first slope is being represented by this purple or violet straight line over here, and the second slope is being represented by this what, the steel color or cyan color uh, straight line over here, okay? So what we'll do is that, okay, for the Heinz method, we are providing them equal weightage, right? So we are going to provide both of these slope values equal priority. So we are basically multiplying a weight of half with them, right? So when we do that, what essentially we come up with is something like this. Let me use a different color for this. So let's say of course, our weighted slope value will start from this initial point right here. Okay, so this, for the value of this slope and the value of this slope divided by 2 may look something like this. So I'm of course eyeballing it. So it might look something like, say, this. Okay, so that, I think that's good enough. Okay, so if we this slope, this straight line that I have drawn using the green color, it's not as upright as the straight line that I have drawn using the cyan color, and it's not as bent down as the straight line that I've drawn using the purple color, right? It maintains a slope that's somewhere in between, right? So that's kind of my eyeball drawing of the average of the straight line with an average slope of these two slopes. Okay, fine. So what we'll say is that, okay, this straight line, green straight line over here, has a slope of what? Half of k1 plus half of k2, right? Okay, so now that we have come up with this new straight line over here, let's see what approximation of the uh, y sub I plus 1 becomes. Okay, so we have seen that, okay, we have approximated our y dependent variable y value at the x sub I plus 1 point as something like this, right? So that this was an approximation. So using our average slope straight line, we'll come up with a better approximation, which is somewhere over here, right? So if you project the value at the point x sub I plus 1 if we project it upwards a bit more. So instead of stopping here, we are going to stop at the straight line, green straight line, okay, the average slope straight line that we have just come up with. And we say that, okay, at this point will be our y. So this particular coordinate over here will be what? X sub I plus 1, comma, y sub I plus 1, okay. So the value of y sub I plus 1 is being approximated in this manner. Okay. So this is basically the y sub I plus 1 that we're trying to come up with. So we say that, okay, whatever values of slope that we get for k1 and k2, we'll take the average of them. That will be the slope of my new straight line. So this whole thing is the slope of the new straight line. We have our x value as h. So this whole disparity is h if you consider the first the initial point as being coincident on the origin, and take the average value straight line, average slope straight line, and whatever the point of intersection that we come up with between this new straight line and the x sub I plus 1 point, that will be our uh, y sub I plus 1 approximation. Okay, fine. So I hope you understood this one. So we'll again explore this same concept for the midpoint method as well. I think it will be a bit more clear when we do that. Okay, fine. Let's go back to our slide and see what the midpoint method is all about. Okay, I think you guys have understood the Horn's method by now. The simple assumption is that we'll assume the value of a2 to be half, which of course implies that the three other unknown quantities will be a1 equals half, b equals to 1, and q equals to 1. If we know all four of these unknown values, we can simply plug them into our compact form of the RK2 method formula and come up with the respective slope values for the k1 and k2 slope values for the k1 and k2 respective k1 and k2 values, and we can use those k1 and k2 values to come up with a average sloped straight line, which I have drawn using this green line over here, and use that particular straight line, that resultant straight line, to approximate my value of the dependent variable y at the after the I plus 1 step. Okay, so notice that we are calling it step and not an iteration, right? Because while performing iterations, we are trying to refine a certain quantity. Okay, whereas in case of algorithms that are concerned with solving ordinary differential equations, we call them steps instead of iterations. Okay, so let's go back to the slide and see what else we can do. Okay, now that we are back to the slide, so this slide basically depicts the same information that I have talked about in our bamboo paper just a bit a while ago. Okay, so we have of course skipped some algebraic steps, some lengthy algebraic steps, while equating the coefficients of this equation and this equation right here, right? So if you are, I'm reiterating, if you're interested on the actual proof, you can check out the appendix a part of the lecture note. Okay, it's at the very tail end of the lecture note. The proof is very big, so of course it will not come in the exam. Just to be just to make sure it will not come in the exam. You can rest assured about that. But if you are interested on how the flow of things came about, you can basically check out that proof. Okay, that proof basically utilizes the Taylor series for bivariate functions. Okay, so up till now we have only learned the Taylor series for a univariate function, right? For a functional value at the point x plus h, right? So for that, for the bivariate functions Taylor series, we need to come up with the functional value at the point what? So it looks something like say this: f of x plus a and y plus b. Okay, instead of say what so far we have learned the Taylor series for something like this, right? F of x plus h. For the bivariate function version, we need to come up with the Taylor series for what? F of x plus a and y plus b, right? So I'm basically not discussing it further because beyond the scope of this course. But of course, if you're interested in the underlying mathematics, you can of course check out the proof. Fine. So we have seen that after equating the coefficients, we come up with these three equations, and in order to come up with the values of four unknowns by solving three equations, we need to de facto assume the value of one of the unknowns. Okay, so conventionally we assume the value of a2, and we call it call the methods what Hines method, midpoint method, and the Ralston's method respectively when we say that the values of a2 are half, 1 and 2, 2 by 3 respectively. Okay, fine. So we have already talked about these. Now we have also talked about the Hines method, and we have shown the graphical representation in our demo paper just a while ago. You can look at this figure if you want. That's the same figure. Okay. If you are wondering why there is a big disparity between the actual function and the xi comma yi value over here, you can recall the concepts of what the global and the local truncation errors, right? So while arriving at the point after the ith iteration, it has garnered a lot of, or it has accumulated a lot of global truncation error, okay, which is why there is a significant disparity between the actual functional value and the point xi comma yi, okay. So that's why there's a whole disparity over here. In my bank paper, in the example that I've shown in the memo paper, I have assumed that up till the ith iteration, I did not encounter any truncation error, which is why the point yi that I have considered it basically aligns with the actual function. Okay, that thing is a matter of logistics. Fine. Okay, so matter of specifics. Okay, fine. So now let's talk about the midpoint method. Okay, so in the midpoint method, what we do is instead of considering the value of one a2 to be half, like the advanced method, we consider the value of a2 to be 1. Okay, so when we consider the value of a2 to be 1, let's go back to the equations. These are the equations, right? So we know our value of a2 is 1, which means our a1 value will be 0, right? Otherwise this equation will not be true or will not be satisfied, right? So we say that okay, if a2 is 1, a1 will for sure be 0. Now if a2 is 1 and we see that after multiplying with p we get half, we can say that the p value of p is half, right? And same goes with the third equation. Since our value of a2 is 1, we can say okay, only by multiplying it with only by multiplying 1 with half we can get end up with the product half, right? So the value of q will also be half as well. And I am reiterating again, I am not considering the subscript values p sub 1 and q sub 1 because in my opinion you don't really need this. Okay, I'm just calling them p and q. Fine. Okay, so now that we know the values of all four of the unknowns a1, a2, p1, p and q, we can basically plug them into our formula, right? So let's go back to our mem paper and talk about the graphical representation along with the formula. Okay, a compact version of the RK2 formula. Fine. Okay, so let's go to the next page. Oh, I think I'm done. 100 out of 100, right? So I have to open a new notebook. Okay, let me do that. Okay, so I think this will do. Let's open it. Okay, so now that we are back, okay, now what was our goal? Our goal was to discuss the midpoint method, right? Okay, so for the midpoint case, midpoint, fine. In the midpoint method, we say that okay, our value of a2 is what 1, right? Which means our value of a1 will be 0 because a1 plus a2 is 1. It will only be possible when the value of a1 is 0. Fine. And we have also seen that what a2 times p was half, right? And since we know a2 to be 1, we can say okay, the value of p is half because only 1 times half is half, and we can say the same for q as well. Okay, so the value of q is half as well. Fine. So uh, a bit of observation here is that we have set our first weight value as 0, right? Which means we are not giving any priority to the first slope value. Okay, the slope value k1 that we'll end up with will not pay any heed to that. Okay, the weight of that slope value is 0. We are putting our utmost faith in the second slope value. Okay, so we are giving all the weight to the second slope value, which is why the value of a2 is 1. But why is it called the midpoint method? Let's draw the graph. Let's visualize the graph and see why that's the case. Okay, so we have come up with the four unknowns. We know the coefficient values now. Now let me rewrite the equations over here for better clarity. Let's see what they look like. So y sub I plus 1 becomes what? Y sub I plus what? The value of k1 is 0, right? 0 times k1 plus half times, sorry, 1 times k2, right? And we have h multiplied with it. So we can say that it's something like this. So y sub I plus 1 equals y sub I plus, so this thing will get nullified. We have just k2 times h. Okay. So whatever straight line, the final straight line that we're considering in order to approximate the value of y sub I plus 1, we are saying that the value of that straight line will be exactly equal to the value of the slope of that straight line will be exactly equal to the second slope value, okay, in this case of 2, right? Fine. So now that we know this, let me rewrite the value of k1 as what? That where k1 was the functional value of the bivariate function at the point xi comma yi, which means it's the slope at the point xi comma yi, right? And we have the slope of the original equation at the point xi comma yi. And for k2 we had what? So we considered the k2 to be the slope at a particular intermediate point, right? So in the case of the midpoint method, what we end up with is something like this, right? So the functional value of the bivariate function at the point what? Xi plus half of h, which means we are progressing towards the right by half of the step size, right? Which means we are at the midpoint between xi and xi plus 1. Okay, when I will draw the graph, it will be clearer. I have mistakenly put the bracket over here. So it will be comma, and then we have to put the coordinate value, right? So it's yi plus, we know the value of q to be half as well. So half times k1 times h, right? So of course, just like before, the first slope value that we are coming up with will be used inside of the second slope. It will be implicitly involved in determining the value of the second slope value, right? Because this first slope value is giving me an approximate value of the dependent variable y at the point x sub I plus half h, okay, which means if we progress halfway towards the right, if we go halfway to ahead, whatever value of x that I get at that point x, whatever the value of the dependent variable y is, we get an approximation of that value, okay, when we do that yi plus half times k1 times h, okay. So we have found the equations for k1 and k2. Now let's try to graphically represent them. So let me draw the Cartesian axis here. So again, I'm very bad at drawing straight lines. It looks something like this. Fine. So of course this x-axis will give me the values of x, and the y-axis will give me the values of the dependent variable y. Okay, and our x is our independent variable, right? Okay, so let me draw the curve. So of course the curve that we are drawing is unknown to us. For the sake of illustration, I'm drawing it. Okay, so let's say it looks something like this. Okay, fine. First try. Okay, so let's say we have a particular value of, we have reached the particular value of x after the ith iteration. Let's call it x sub I, and let's assume that we have not garnered any truncation error for the sake of uh, easily understanding the concept. Let's say that okay, this value over here is my value of the dependent variable y at the point xi, right? The exact value. Okay, so what are we going to do? We can also say that since we have not garnered any or accumulated any truncation error, this point over here is my xi comma yi point, right? So my approximation and the exact values are exactly equal. Right. So now that we know this coordinate, what we do is we find the value of k1. So ultimately we don't have the need for k1 in our final compact form of the equation. We just need the value of k1 to come up with the value of k2, right? Because k1 is being used over here as well, right? So we need to find the value of k1. So how do we find the value of k1? We'll basically find out the functional value of the bivariate function f of xy at this particular point xi comma yi, right? Because k1 is equals to f of xi comma yi. So let's say the slope looks something like this. Okay, so let me eyeball it again. So let's say it looks something like this. Okay, fair enough. This one. So this thing over here, let's call it K1, right? Okay, so now our target is what? Our target is to progress by one step size, right? So let's call this point the x sub I plus 1, which is one step ahead. So basically the distance between these 2 points is h, right? One step ahead of x sub I. Okay, so if we project it upwards, will end up here and at this point over here, right? So we don't need the corresponding y values now. What we need is the corresponding y value or the approximation of the corresponding y value at the exact midpoint, okay, or the middle point between xi and xi plus 1. Because for finding the value of the slope k2, we need the functional value of the bivariate function at that particular point, right? So let's say, okay, xi plus half h, which is somewhere over here, that means a different color. So let's say it's somewhere over here. So I'm eyeballing it again. So let's say it's somewhere over here, right? So this thing over here is what? Xi plus half of h, right? Fine. So this thing is the midpoint between xi and x sub I and x sub I plus 1. So if we project it upwards, we end up with the value here, right? So what we say is that, okay, the value of this y, the value of this coordinate over here is xi plus half h, because our abscissa is xi plus half h, comma, this is our abscissa, and our ordinate is what? Yi. So this is of course our y-intercept if we consider this part to be our uh, aligned with our y-axis implicitly. If we consider this thing to be, let's say, if we consider this part to be our origin, this whole part will be our y-intercept, right? So if we say it as something like this, we can say, okay, yi plus, this is the y-intercept, plus we have the value of the slope, right? We have the value of the slope k1, right? So it will look something like this: yi plus half times k1 times h, right? Because h is our x value in the context of this part over here. Fine. So this is the exact coordinate at this point, the point that I am hovering over with using my cursor. So at this point, I need to find the value of the bivariate function. Okay. So when we do that, we will come up with our value of k2. Okay. So let's do that. So let's use a different color. Okay, so at this particular point over here, let's say the value of my bivariate function is what, this thing over here, right? F of xi plus half h comma y plus half k1 h, right? So at this point, let's say the slope will look something like this, approximately, of course, right? And it will be a bit more upright. Oh, I'm so bad at drawing straight lines. Okay, nice one. So this thing, this straight line approximately gives me the slope at the point xi plus half h comma yi plus half times k1 times h. Okay, so let's dub this slope as k2. Okay, the slope of this straight line as k2. Fine. So now that we have our values of k1 and k2, what do we do? We say that we will take a weighted sum of these two slope values, right? Now in the case of the midpoint method, I think by now it's clear why this is called the midpoint method, right? Because the value of k2 that we are coming up with is at the point xi plus half h. Okay, it's at the midpoint between the two adjacent x values, two adjacent values of the independent variable x. Okay, fine. So we know why it's called the midpoint now. Okay, so let's see what we can do with these two slope values. Okay, We know we have already seen that the value of a1 is 0 and the value of a2 is 1, right? Which means we are not paying any heed to the first slope value, and we are giving all the importance to the second slope value, right? Which means the weight of the first slope value is 0 and the second slope value is 1. So what do we do? So since this was our initial point, we'll say that okay, the final line that I'll come up with, let's mark it using green in order to maintain consistency with the Horn's method. So let's say the straight line that I will come up with at this point, that slope of that straight line will be exactly equal to the slope of this straight line that I have drawn using the, say, the sky blue color, right, or the azure color. Okay, so what will I do? I'll say that okay, this straight line that I'll start drawing from here will be exactly parallel to this straight line, right? Because they have the same slope, right? Fine. So it will look something like this. Of course, not like this. Of course, not like this either. Let's say something like this. Say I'm not being able to draw a parallel line, unfortunately. So roughly like this. So of course, these two lines are parallel. Okay, fine. So let me mark it. Okay. So these two lines will of course be parallel. Fine. So because of course the value of the straight line of this green straight line, the slope value of the slope of this green straight line is what? 0 times k1 plus 1 times k2, right? Which is say the same as saying just k2, right? Slope of this straight line is k2 and the slope of the blue straight line that we have come up with was also k2. So these two straight lines will of course be parallel. Fine. So now that we have made that point clear, what do we see? We see that okay, this green straight line, where does it intersect with the value of the where does it intersect when I take the value of the independent variable to be x of I plus 1. Okay, so let's project it upwards just like before. We see that it intersects this point, this straight line at the point, at this red point over here, right? So we call this red point as our next approximation, okay, or we call it as our y sub I plus 1. I think by now it's probably clear to you why we say that okay, y sub I is our y-intercept, this thing over here. If we take this point to be our origin, and we take this k2 to be our slope. So this k2, the straight line of this green straight line over here, it has a slope of k2, right? And this h over here is our abscissa value, right? Because we are progressing towards the right by h units, right? In order to arrive at the point x sub I plus 1. We say that okay, the value of the ordinate at this exact point x sub I plus 1 will be a y sub I plus 1, which I will get by plugging in the corresponding values at this straight line equation over here. So what do we get? We get the corresponding y sub I plus 1 value at the point where this projection intersects with the straight line. Okay, so this thing is our approximation of the dependent variable y after the I plus 1 step. Fine. Okay, so now we know how the RK2 methods formula in the case of the midpoint method manifests, right? So this thing was our formula for the midpoint method. So if we go back to the previous segment of the video, we derived the formula for the Horn's method, right? And we also did the same thing for the generic or RK2 method, right? Where the weights were given as A1 and A2. Right? So now that we know how to utilize the midpoint method, let's talk about the Ralston's method in brief, because I think by now you get the gist of the idea, right? We just get start with different presumptions, which means we take the value of a2 to be different as a presumptive notion. We take the value of a2 to be different in the different cases, right? So in the case of midpoint, we take it to be 1. In the case of Heinz method, we take it to be half. And let's go back to the slide and see what we do for the Ralston's method. Okay, I think it was 2 by 3, right? Okay, so yes, it was a2 equals to 2 by 3. So when we take the value of a2 to be 2 by 3, we can easily come up with the rest of the three unknown values, right? So since we know the sum of a2 and a1 will for sure be 1, we can say that the value of a1 is 1 by 3, and the value of p is 3 by 4, because a2 times, sorry, 2 by 3 times 3 by 4 gives me half, right? So the value of p will be 3 by 4 and the value of q will also be 3 by 4 as well. Okay, fine. So again, I'm reiterating. So I'm calling p sub 1 and as p and q sub 1 1 as q because in my opinion, you don't need the subscripts, but in Professor Author Cow's lecture notes, he has used these two subscripts without mentioning the actual reason. So for now, I'm just calling them P and Q. Okay, fine. Okay, so we know for the value of Ralston's method, in the case of the Ralston's method, we have these four unknown coefficient values, right? So what we can do is simply we can plug them in just like the preceding two methods, midpoint method and the Hines method. We end up with what the weight values of 1 by 3 and 2 by 3 respectively for the weight values A1 and A2. And in the case of the while finding the slope at the second point or at an intermediate point between xi and xi plus 1, what we do is, okay, the value of the slope k2 will be the functional value of the bivariate function at the point xi plus 3 by 4h, which means we progress 75% of the pathway between xi and xi plus 1, which means we progress by three-fourths of the step. Okay, instead of half of the step that we did in the case of the midpoint method, we go ahead by three-fourths of the single step, right? Okay, so that's the abscissa value and the corresponding ordinate value, which means the approximation of the dependent variable y at that particular point will be something like this. It involves the value of k1, right? The value of k1 will be same, just like before. It will be the functional value of the bivariate function at the point x sub y and y sub I. Now we'll use that k1 value to come up with the approximation for the y value in the case of while calculating the value of k2. Okay, so the ordinate value will be y sub I plus 3 by 4 times k1 times h. Okay, so these will be our respective equations for the Ralston's method. Okay, so in the exam, if I tell you to use a particular method, I think by now you're kind of clear on how to use which method. Okay, you just take the assumption to be different in case of each of these different methods and you're good to go. Okay, if you just remember the three equations and the initiating or the initial values of the A2 that are assumed in each of these methods, you're good to go, right? Fine. Okay, so now that we know the three approaches that are used to come up with the formula for the RK2 method, let's try to apply one of them. Let's try to apply this RK2 method and use one of those approaches to solve this exact same problem that we have solved in our last lecture, right? In our lecture 14, I think, in our Euler's method lecture. So this was a simple thermodynamics problem, which was what we have a heated ball which was heated up to 1200 kelvins. It was allowed to cool down at a room temperature, ambient temperature of 300 kelvins. Okay, so the heat or the temperature decline of that ball was dictated by this first order differential equation over here. Okay, so we say that the change of uh, the temperature theta with respect to the change of time was something like this. We call it the ddt of theta, right? It was something like minus 2.2067 times 10 to the power minus 12 times theta to the power 4 minus 81 times 10 to the power 8. We have a leading minus because we know that the temperature will gradually decrease over time, right? Instead of increase. So uh, whatever change we have, it will be in the negative direction, right? Fine. So of course the value of the temperature is in kelvins and the value of t is in seconds. Okay. So the question asks us to find the value of the temperature at t is equals to 480 seconds, just like before. And this time we'll use the RK2 method instead of the Euler's method. Okay. And it also tells us to take take the value of h or the value of the step size as 240 seconds, right? So since we have to calculate the value at 40 seconds, we can simply say that, okay, we need to perform two steps of the method, right? Because from in the first step we'll go from 0 to 240 and in the second step we'll go from 240 to 480, right? So we'll have to perform two steps of the calculation. Fine. So let's see how to do that. So for this problem, we'll use the Hines method. So in the Hines method, we take the value of A2 to be half, right? If you want to use any other method, say the midpoint method or the Ralston's method, just take the initial value of the A2 to be different. Okay, so whatever weightage that you are giving to the second slope value, just take it to be different. The corresponding A2 value, say for the midpoint we take it to be 1, right? And for the Laplace method we take it to be 2 by 3, right? So you take that and put the respective equations and you're good to find. So okay, for this problem, what do we know? We know the differential first order differential equation that has been given to us, and we say that okay, well, let's express this slope value or this slope equation using a bivariate function, right? Which means by bivariate we means it changes with two variables, and in this case our first variable is t, which is time in seconds, and our second variable is theta, which is temperature in kelvins. Okay, fine. So we have to express this at the first order derivative as something like this as a bivariate function. Now we can simply apply the RK2 formula for the Foynes approach. We get something like this, right? We got y sub I plus 1 equals y sub I plus half times k1 plus half times k2 times h, right? Now in the case of this specific example, we are replacing the value of the dependent variable y with theta, right? With the notation theta, because in this case the dependent variable is the temperature variable, right? Because the temperature changes with respect to the change in time. The time is independent; it will change on its own accord, but the temperature will change with respect to the time, right? Fine. So we have what our formula is: theta sub I plus 1 equals theta sub I plus half times k1, which means we are giving an importance of half to the k1 and an equal importance to the k2, which means half times k2 times h. Fine. So we also know our value of k1 and k2 will be the functional values of the bivariate functions at the point t sub I and t sub I theta sub I for the k1 case, and for the k2 case we have the functional value of the bivariate function at the point t sub I plus h, which means we progress by h units to the right, and we have the corresponding approximation of the dependent variable theta at that point, which is theta sub I plus k1 times h, right? So we use this we use the functional value at this coordinate, at this particular coordinate, in order to come up with the slope k2. Okay, so once we have the values of k1 and k2 at our disposal, we can basically proceed to the next iteration, or the next step, my bad. So it will be the next step. Okay, so let's start with the step 1. In step 1, of course, our I will be 0, because our initial condition has what? The temperature at the time t is equals to 0 seconds, right? So the ball was heated up to 1200 kelvins, and the cooling started from time t is equals to 0 seconds, right? So the initial temperature of the ball was 1200 kelvins, right? So at time t is equals to 0 seconds, we had a temperature value of 1200 kelvins. So we know our theta 0 to be 1200 kelvins, right? This is our initial condition, and we know our I value will be 0, right? So our T1 will of course be one step towards the right, which is at 240 seconds, we are taking the value of H to be 240, of course. And for calculating the value of K1, for calculating the value of k1, we find the functional value of the bivariate functions f of t comma theta, which is this bivariate function over here at the point t naught and theta naught. Okay, so we know our t naught to be 0 seconds, and we know our theta naught to be 1200 kelvins, right? According to our initial condition, if you plug them into your calculator, you'll get something like minus 4.5579. Okay, and for the value, for finding the value of k2, we do the same thing. What we do, we just plug in the values, so 240 and 106.09, we find the functional value of the bivariate function at this particular coordinate. If you use a calculator, you should get something like 0.017595. Okay, so these two are our slope values. Now what will we do? We will give them equal importance. Okay, so we plug these two slope values in this equation over here, and then see what we get. So okay, so in order to find the value of theta 1, which is the value of the temperature that we get after performing the first step, what will we do? We'll use the theta naught value, and we'll use this formula over here. You plug them into your calculator, you get something like 655.16 kelvins. Okay, so we say that okay, this is my approximation, but this is the value of my dependent variable theta at the after performing the first step at the midpoint. Okay, so at the, so not at the midpoint, after performing the first step, okay, at theta 1, at the theta I plus 1. So since the value of I was 0, it will be I plus 1 will of course be 1. So the value of theta 1, the approximation at that point, after performing one step or going one steps ahead towards the right, we get 655.16 kelvins. Okay, this is my approximation at the point x equals to, or sorry, the at t equals to 240 seconds. Okay, now we need to perform one more step, because our goal was to find the value of the temperature at t equals to 480 seconds, right? We have only come up with the value of the temperature at t equals to 240 seconds. Okay, so we need to perform one more step, which means we need to progress by one more step towards the right, and our step size is of course 240 seconds. So let's perform the one more step. We say that okay, our T1 will be our T2 will be T1 plus H, right? So 240 plus 240 we get 480. Our value of I will of course be 1, and from our previous step we have found the value of theta 1 to be 655.16 kelvins, right? Okay, so now that we know all these given all these values, what we can do is we will use the same set of steps in order to come up with the value of k1 and k2 respectively. Okay, so for finding the value of k1, we need to find the value of the functional bivariate functional value at the point t1 comma theta 1, which we get at something like minus 0.38869. Okay, and for the value of k2 we do that we progress towards the right by one step, which means t1 plus h, which was 480 as we have found out over here, and theta 1 plus k1 times h is something like 561.87. Okay, so we find the functional value of the bivariate function at this particular coordinate over here. If you plug the respective values into your calculator, you should get something like minus 0.20206. Okay, so we know how to calculate the k1 and k2 values now. Now our job is to plug these k1 and k2 values into our equation, our RK2 method equation in the case of the Hans method, and we'll see what final approximation we end up with. Okay, so of course our theta 2 will be our final approximation because we have already arrived at the t equals to 480 seconds mark, right? Okay, so theta 2 will be of course theta 1 plus half times k1 plus half times k2 times h, because we are providing equal weightage to both of these slope values. So if you plug in the respective values into your calculator, so theta 1 was what? We have already calculated theta 1 in our previous step, right? And if you plug these respective values into your calculator, you should get something like 587.27 kelvins. Okay, so we say that okay, the value or the approximation of the temperature at time t is equals to 480 seconds is something like 584.27 kelvins. Okay, so the temperature is of course gradually decreasing, right? So from 1200 kelvins it became 655.16 kelvins approximately after 240 seconds, and after 480 seconds it became even lesser. It became 584.27 kelvins, right? Fine, so let's see how this approximation fares with the exact value. Okay, let's compare it with the exact value and see how good we did. So if you recall from our last lecture, the value of the exact value of the temperature at the time t is equals to 480 seconds was the solution or the root of this nonlinear equation over here. Okay, so if you analytically find out the root of this nonlinear equation, you should get something like 647.57. Okay, so this amount of kelvins will be my temperature at the point at the time t is equals to 480 seconds. Okay, so since this is my exact value and this is the approximate value that I have come up with after 480 seconds, after performing two steps of my RK2 method using Heinz approach, we can say that okay, these two values are very far apart, right? So whatever approximation that I have come up with is somewhat good or not a very good approximation. Okay, it depends on your standard basically. So one thing that we can do is okay, why not decrease the step size, right? So okay, so see over here what we have ended up with is this point over here. So while taking step size as 240, we have ended up with this point over here, whereas the exact value is something what more than 600, right? So whatever we did was somewhat say a somewhat good value, right? Somewhat good or not that good. Of course, it depends on your benchmark, right? Okay, so one commonsensical thing to see is that one, it doesn't take very special intuition to see that if we take the step size to be very large, it will give me a very bad approximation, right? The exact value is somewhere over here. I get the approximate value as negative something, right? We have seen this thing in the case of the Euler's method as well. So one salient thing to do is to decrease our step size, right? So if we decrease the step size by half, if we take it as 120, we get an approximation which is very near to the exact value, right? It almost coincides with the actual value, right? So if you see this dotted line over here, it almost perfectly aligns with the exact value, which is a non-dotted curve, right? It almost aligns with that. So for if we take lesser and lesser step sizes, we'll come up with better and better approximations. Okay. So that trend is basically depicted in this table over here. So whatever step size we take, if we decrease it by half each time, we end up with values of theta, or the values of the temperature at the time t is equal to 480 seconds, as something like what? As something very close to the exact value 647.57 kelvins, right? So see, for the step size 30, we get 648.21 kelvins, right? Which is very near to the exact value. And value of the true error and the value of the relative absolute relative true error gradually decreases while we decrease the step size bit by bit, right? Or if we decrease the step size by half each time, right? So one salient thing is to decrease your step size if you get a very big error. Okay. So the effect of decreasing step size is of course the extra computational overhead, which means you have to perform more steps to come up with the approximation, right? So this is the trade-off that you have to maintain. Okay, you have to sacrifice some accuracy for your computational overhead if you want. Okay, so okay, so this is what the graph looks like. So for ever increasing step size, we come up with more unhinged approximations, right? So one for 480, for step size 480, we get an approximation of minus 393.87. Okay, which is nearly impossible. Fine. So okay. So now that we have discussed this trend over here, let's try to compare the RK2 method with the Euler method. Okay, so if you recall, in our Euler method, we ended up with these sets of values, right? For 480, we had minus 987.84. Yes, so sorry for that. Okay, so at while taking the step size h as 480 seconds, we have seen that our Euler's method gives us a very bad approximation of minus 987.84, right? So which is basically what very unhinged approximation, right? So compared to that, other our RK2 method approaches are giving me somewhat closer approximations to the actual value, right? So when our actual value was 600, if you recall, it was 647.57 kelvins, right? Okay, so these three values are better approximations, of course, with a very big step size of h. Now, if we go to the extreme low end, so when we take the step size of h to be step size h to be 30 seconds, we see that our Euler's method comes very nearly close, but not as close as the approximations that have been generated in the case of the Hoyt midpoint and the Ralston methods. Okay, so if you look at this graph over here, this graph tries to compare all four of these methods. So if you look at the black curve over here, which is, I know, almost superimposed with the cyan colored line, cyan colored graph. So this black curve over here is the exact value curve, or the analytical curve of the temperature, of the relationship between the temperature and the time. Okay, for that, this particular example of this heated ball being cooled off at ambient temperature. Okay, so you can see that the approximations generated by the Euler's method is very far apart, right? It's garnering a lot of truncation error at each step, right? Okay, so at the point at time t is equals to 480 seconds, it comes with whatever approximation that it comes up with is very far apart from the exact value compared to the other three methods, right? So if you look at the, let's say, what's the best method that's working for this particular example, we can say that with a great degree of certainty, we can say that it's the Hoynes method, right? Because the Hoynes method curve is actually coinciding or very closely aligning with the actual analytical curve, right? So that does not uh, de facto mean that the Hoynes method will be the best method in all specific cases. Okay, there are of course examples that you can come up with where the midpoint method will work better than the Hines method, or where the Ralston's method will work better than all the other methods, right? So for this specific example, or for this specific thermodynamics problem, what we see is that the Hines method performs nearly as good as the exact analytical curve, right? Fine. So okay, so now that we have compared all four of these methods, you have kind of a good idea, right? Why the second order method is better than the Euler's method, right? So the more the terms of the Taylor series that we take into consideration, the better the approximation of we'll get for the dependent variable y and particular discrete values. Okay, so in this specific example, our particular dependent value was our temperature theta, right? So as we progress forward, the better and better approximation that we got, right? So of course we'll accrue some truncation error at each step for each of these methods. But if you take more and more number of terms from the Taylor series, if you consider that, and if you can come up with a particular approximation equation, just like Runge-Kutta did for the second order and the fourth order cases, you can basically sidestep that overhead that you need to uh, undergo in order to calculate the derivative values f prime, f double prime, and f triple prime, right? If you can sidestep that computational overhead, you can of course come up with very good approximations, right? Fine. So now let's talk about the Runge-Kutta fourth order method. Okay, of course we'll call it the RK4 method from now on. And this method is just like the RK2 method, just it in order to get better approximations at each step, what it does is it considers two more terms from the Taylor series. Okay, so instead of considering the first three terms, it considers the first five terms. Okay, so let's talk about that the derivation part a bit later. Now let's try to understand the theory. So the theory is that okay, it's yet another numerical algorithm to solve first order ODEs. So of course the form will be something like this: dy dx will be a bivariate function f of xy, where where an initial condition has to be given to us. Okay, so we need to know the value of the dependent variable y at a particular point x naught. Okay, where the value we're calling it as y naught. Okay, and just like all the other preceding methods that we have discussed, the RK4 method is also applicable only for first order ODEs. Okay, and while solving the first order ODEs, we need to cast it in form of this template over here. Okay, so whatever first order differential equation we have, we need to make sure that it fits this template over here. So on the left hand side of the equation, we have to have the differentiation ddx of y, and at the right hand side we can have the rest of the terms, which will basically be a bivariate function with two variables x and y. Okay, and a small caveat is that x is the independent variable and y is the dependent variable that is reliant on x. Okay, y is a function of x. Fine. So now that we know the theory behind the RK4 method, now let's see how to derive the formula. Okay, and the derivation approach is the same as before. So instead of in the Euler's method, we consider the first two terms. In the second order method, the RK2 method, we considered the first three terms, and in the case of the RK4 method, we will consider the first one, two, three, four, five terms. Okay, so why do we call it the fourth order method? Because at the fifth term, you can see we are calculating the fourth order derivative, right? So d4y by dx to the power 4, right? This is the fourth order derivative of the dependent variable y, right? So when we cast it in the form of the bivariate function, we say that it's a third order derivative of the bivariate function, right? Okay, so now that we know what the formula for the RK4 method is, it looks something like this, right? When you consider the first five terms, it will of course look something like this. Now again, the obvious pitfall here is that you need to calculate the value of the first order derivative, the second order derivative, and the third order derivative of the bivariate function f of xy symbolically, right? And we know when we try to do that, it starts to get out of hand real quick, right? The code that you need to write in order to calculate these, it starts to get real big when the structure of the equations are different, right? So we need to come up with some sort of way with which we can approximate this part of the equation. Okay, so it has to be yi plus something, where something has to be replaced by what, an approximation part. Okay, so instead of calculating these exact values of the derivatives, we need to come up with an approximation part. So let's see what Runge and Kutta did, what Carl Runge and Wilhelm Kutta did to basically sidestep these computational overheads. Okay, fine. So So what I'll do is that I'll try to avoid writing the equations in my bamboo paper because the equations are really really big. I'll try to show them from the slide over here. Okay, so just follow along. It's very easy. Okay, so let's proceed. So how do we derive the actual approximation formula? We have said that okay, we don't want to calculate these higher order derivatives symbolically because it incurs a lot of computational overhead on our part. We'll try to approximate it as something like this. Okay, so what Mr. R and Mr. K did was they recast this whole equation as something like this: yi plus 1 equals yi plus a1 times k1 plus a2 times k2 plus a3 times k3 plus a4 times k4 times h. Okay, so what's happening over here? We are taking four different slope values at four different points, of course, and we are assigning weights of a1, a2, a3, and a4 to them respectively. Okay, so just like before in RK2 method, we found out slopes at two different points, right? And we have given them weights according to different approaches, right? A1 and A2, right? And in the RK4 case, RK4 methods case, we calculate the slopes at four different points and we give them their respective weightage in order to calculate the approximate value of this whole these four terms in total. Okay, fine. So again, the concept is similar. If you take this yi value as the y-intercept, and if you take this weighted sum of all the slope values as the slope of the new straight line, and this h value as the transition that you make along the x-axis, or the units with which you traverse along the x-axis, you can say that okay, my according to my straight line formula, we can say that y equals to mx plus c will be my whatever value that I come up after solving that equation will be my new approximation and after the I plus 1th step, okay, which is y sub I plus 1. So I have, for the sake of understanding, I have included the figure, the formal figure for the RK2 methods midpoint approach as well. So I have already drawn this a similar figure to this in our bamboo paper, right? So what do we do in the case of the midpoint method? We calculate the value of K1 at this initial point, the slope at this initial point, and we perform the same step at an intermediary point. That's exactly the midpoint between the xi. So they have used the notation t. So for the sake of consistency, let's call it xi, and this is xi plus 1, right? The actual midpoint is xi plus half h, right? So at this particular abscissa, they approximate the value of y to be something somewhere over here, this point over here, right? And they calculate the slope of the curve, the unknown curve that we have at this particular point, right? Because we don't know the actual curve, we know the bivariate function that dictates the slope of that curve, right? So that slope of that curve will be k2 at this point, right? So we take the value of k1 and k2 and we take a weight of a1 as 0, so we don't pay any heed to the k1 value. We take the entirety of the k2 value as the slope value of the slope of our final straight line, right? So if you to look at this final dotted straight line, which is colored in red over here, this is exactly parallel to this straight line over here, right? So the entirety of the slope value k2 will be the slope value of this new dotted straight line, which is in red color, and whatever value of y that we get for this straight line at the point xi plus 1 will be my approximation of the value y sub I plus 1 at the point x sub I plus 1. Okay, and we proceed from there and so on. Okay, fine. So this was the midpoint method. Now what we do in the case of the RK4 method, we do, instead of calculating the slopes at 2 points, we do it for slopes at 4 points. Okay, so the k1 will be of course at the initial point over here, the k2 will be at some point over here, the we'll see why the k3 slope is a bit above the k2 slope. We'll see it in a bit. Just understand what we're doing here in essence. In essence, what we're doing is we're trying to find the slope at point, this point over here, at this point over here, at this point over here, and this point over here. Okay, so we have found four slope values, right? K1, K2, K3, and K4. Now we take a weighted sum of these four slope values and we come up with a straight line with the slope that looks something like this. Okay, this red dotted line over here, and just like before, whatever the whatever point that we get for this final straight line and the point xi plus 1 will be our approximation of the value of y sub I plus 1, okay, or the value of the dependent variable y after the I plus, after committing or after executing the I plus 1 step, okay, which is this red point over here. Fine. So of course the actual value will be somewhere over here where this blue curve exists for this point, and we're getting an approximation of something like over here, right? Fine. So now let's go to the actual details of the equations and see why these points are where they are. Okay, these green points are where they are. Okay. Okay, so there are basically two approaches of coming up with the final formula of the RK4 method. So one was developed by the first author Runge, and the second approach was developed by the second author of this method, Kutta. Okay, so both of them are German mathematicians, as we have discussed before. So both of them have come up with two different approaches, to basically come up with the final formula of the uh, RK4 method. Okay, so we have seen that our RK4 method's formula was the compact version of something like this. Okay, so now it rests upon us what do you want the values of the weights to be. So okay, so Runge said that okay, let's take the value the weight of K1 as 1 by 6, the weight of K2 as 1 by 3, the weight of K3 as 1 by 3, because 2 by 6 is of course 1 by 3, and the weight of K4 is 1 by 6 as well. Okay, so if we take the values of A1, A2, A3 and A4 as 1 by 6, 1 by 3, 1 by 3 and 1 by 6 respectively, what we are doing is we are basically implementing the Runge's approach. Okay, and if you see, you can draw a parallel between this 1 by 3 values with the Simpson's 1 by 3 rule, right? So whatever derivation that they showed in their paper, it involves the Simpson's 1 by 3 rule. Okay, and we can also say that okay, if our slope, the bivariate function that we are using to uh, denote the slope equation, right, the dy dx equation, we say that if it was a univariate function of x, we could simply say that okay, we are applying the Simpson's 1 by 3 rule. Okay, and in the case of Mr. Gupta, he did what his approach was something like this. Okay, we'll apply a weight of 1 by 8 to the first slope value, a weight of 3 by 8 to the second slope value, a weight of 3 by 8 to the third slope value, and a weight of 1 by 8 to the fourth slope value. Okay, so again, if you draw a parallel between the Simpson's 3 by 8 rule and these 3 by 8 weights over here, you'll of course see a resemblance, right? And of course, this derivation over here involves the Simpson's 3 by 8 rule. Okay, we are not diving into the derivation because that's beyond the scope of this course. You can of course read the relevant papers, the paper in which they propose this actual method. You can go through that paper if you want to know about the derivation. Okay, you can find it on Google Scholar if you want. Fine. Okay, so now that we know the formulas that Runge and Kutta themselves proposed, what we will do is, okay, we have found the formulas. Okay, now we need to know the uh, points at which we need to find the slopes in order to find the values of K1, K2, K3 and K4. Okay, so in the case of Runge's approach, the value of K1 was the functional value of the bivariate function at the point xi, yi, just like before, and for the finding the value of k2, he progressed by half a step. Okay, so xi plus half times h and yi plus half times k1 times h. Okay, and for finding the value of k3, he also did the same thing again. So what he did was his abscissa was the same. Okay, see, he went ahead to the right by half a step, so xi plus half h, but the ordinate this time was dependent on the value of k2. Okay, so the first ordinate while finding the value of k2, we were using an approximation of the dependent variable using the value of k1, right? But this time for k3, we are using the value of k2. Okay, and we'll visualize these 2 points in just a bit. We have already visualized this actually. We'll go to the previous slide, explain it a bit more clearly. Fine. Okay, and for the value of k4, we basically calculate the functional value of the bivariate function at the final point. Okay, by final point I mean after performing the entire step or the whole of the step, which means xi plus h, whatever approximation of the dependent variable y we get at that point, we say that it's okay, it's something like y sub I plus k3 times h, okay, where k3 is the preceding slope value, right? So the bivariate functional value of the bivariate function at that particular coordinate is what the slope value k4. Okay, so now let's go back to the previous slide. Okay, so now we can understand, right, why k2 and k3, why k3 is on top of k2, right? Because they have the same abscissa value. So this figure is kind of resembling the Runge's approach, right, of the RK4 method, RK4 method. So okay, so K2 had what? The functional value at where the abscissa was xi plus half h. So xi plus half h is somewhere over here, this midpoint over here. And same for K3, the abscissa was xi plus half h, right? And the abscissa is something somewhere over here. So the slope is also somewhere over here. Only they differ at the ordinate values, right? Or the y values, right? So in the case of K2, we use the value of K1. So of course the slope K1 is lesser than the slope K2 over here, right? In this particular example that we have used for visualizing, the the straight line that has the slope K1 is a little bit bent downwards, right? And the straight line that has the slope K2 is a bit uh, upright, right, compared to the first straight line. So of course, if I multiply the value of K2 with h and half and add it with yi, we should get a value that's above the value that we would get if we multiplied half times k times h and we added that value to yi. Okay, so of course this value will be lesser than this value, right? That's why we ended up with the, for calculating the value of k3, we ended up at a point that is above the point that we ended up for the case of k2. Okay, fine. So you can of course look at these equations and this graph and you can basically sort everything out. Okay, very pretty self-explanatory. Okay, fine. So now that we know Runge's approach, we can say, okay, we can also do the same thing for the Kutta's approach as well. Okay, so the Kutta's approach is a bit more convoluted to understand. So his equation is this one, just like we have discussed. His equation for K1 is also the same, but for K2, what he's doing is, okay, he's not progressing by half a step. Okay, he's progressing by one third of a step. Okay, so xi plus one third h, and the approximate value of y at that particular point, considering the value of K1, of course, the preceding slope value. Okay, so that's his K2 value, okay, the functional value at that particular coordinate. And for K3, what he did was, okay, instead of going through one third, now he is progressing by two thirds. Okay, so xi plus 2 by 3 h. Okay, so which means he's going 66.67% of the steps towards ahead towards the right. So that's the abscissa, and this is the particular, let's say, the particular approximation of the y value at that particular point of x. So he wrote it as something like yi minus 1 by 3 hk1. So whatever he added over here, he subtracted it over here, and he added h times k2. Okay, so k2 was the preceding slope value, right? For K3, the preceding slope value is K2 and the succeeding slope value is K4, right? Okay, so that's his value for K3. Now let's talk about K4. For K4, he went all the way towards the right, so he went progressed by one whole step. So xi plus h, and at that particular point, he said, okay, the value of the dependent variable y would look something like this: y sub I plus h times k1. So he uh, added this h times k1 over here, and he subtracted whatever he added in the last preceding slope value, which is h times k2, right? He subtracted that and he added h times k3. So of course k3 is the preceding value for k4, right? And whatever we end up after performing this algebraic operation, sets of algebraic operations, he said that, okay, that's the approximate value of the dependent variable y at the particular point xi plus h. Okay, when the abscissa is xi plus h. Now that we have these coordinate, we can say, okay, the functional value of the bivariate function at this particular coordinate is my fourth slope. Okay, fourth slope value, which is k4. Okay, when we have this k1, k2, k3, and k4 for both Runge's approach and Kutta's approach, we can basically plug them in to our final formula, a compact version of the RK4 method formula. Okay, which is something like this. Fine. So let's try to do that and see part. Let's try to use, let's say for the next example that we'll try to solve, we'll use the Runge's approach and see how we can use the RK4 method to come up with a particular value of the dependent variable at that discrete point. Okay. So let's do this same example that we have done for each of these algorithms. These will be algorithms, numerical algorithms for finding the solution to first order differential equations. So here the problem is the same. We have a heated ball which is heated up to 1200 kelvins, and we are allowing it to cool down at an ambient temperature of 300 kelvins. So basically, the room temperature you can call it. Okay, so we have this temperature. Okay, now the ball will of course lose heat, right, over the course of time, and this loss of temperature, so since it will lose heat, its temperature will also decrease, right? So this loss of temperature is dictated by this first order differential equation over here. So d theta with respect to dt is something like minus 2.2067 times 10 to the power minus 12 times theta to the power 4 minus 81 times 10 to the power 8. Okay, so since as I'm repeating that, I am reiterating that we have a leading minus sign over here because the temperature is decreasing over the course of time, not increasing, right? So it's going towards the negative direction, right? Fine. So again, the value of the temperature is in kelvins and the value of the time is in seconds. Okay. And it asks us, the question asks us to find the value of the temperature theta at t equals to 480 seconds. Okay. And this time, instead of using the RK2 method, we will use the RK4 method. Okay. And the step size is just like the same as before. We'll use 240 seconds as our step size. Fine. Okay. Okay, so what do we know? We know our bivariate function. We know f of t and theta, just like before. It's this thing over here because we have cast this derivative, first order derivative as something as the bivariate function over here, right? And we also know the formula that we come up with for the RK4 method in the case of Runge's approach, right? So for Runge's approach, we found that y sub I plus 1 was equals to y sub I plus 1 by 6 times k1 plus 2 times k2 plus 2 times k3 plus k4 times h, right? So we applied that formula over here. So in the spot of y we are using theta because for this example theta is our dependent variable and time t is our independent variable. Okay, time depends on nothing, right? Fine. Okay, so for our first step, so for executing or for computing, for basically executing our first step, what do we take? We take the value of I to be 0, right? Because we are given the value of theta at time in t is equals to 0 as 1200 kelvins, right? So when we started monitoring the loss of temperature of the ball, it was initially at 1200 kelvins, right? So when you plug these values to your bivariate equations, and use a calculator, you should get something like minus 4.5579. Okay, now that's your value of k1. Now how to find the value of k2? We'll use the formula that we have discussed about, the equation that we need to use for k2 in case of Runge's approach. We'll use that. We know the value of h, we know the value of t naught, we know the value of theta naught, we know the value of k1 because we've already calculated it over here. We know the value of h. You plug them in, you get your functional value at that point, which is 120 comma 653.05, right? This coordinate over here, you get the functional value at this coordinate. You should get something like, when you use your calculator, you should get something like minus 0.38347, right? Okay. So okay, K2 is done. Now let's proceed to K3. K3 you will use the same. We'll use the formula that we have seen in the case of Runge's approach. You'll get something like minus 3.8954, and for K4 you'll use, okay, the value of K3 you'll use, and the rest of the things are already known to us. You should get something like 0.0069750. Okay. Now that we know all four of our slope values, our job is to perform a weighted sum of them, right? Because in our actual formula for the RK2, RK4 method, we're using a weighted sum of all these slopes and multiplying it with h and adding it with the y sub I value, right? Or the theta sub I value in the case of this particular example. So let's do that. So we know what the I is 0, so we are using theta naught. Theta naught is 1200 kelvins, of course. So 1200 plus the weighted sum of all these four slope values that I just got times h, and h is of course 240 because given in the question, right? So if you plug these values into your calculator, you should get something like 675.65 kelvins. Okay, that's your approximation of the temperature value after performing the first step. Okay, we are not done yet, right? So this approximation over here is at the time t is equals to 240 seconds, right? Fine. So it's something like t naught plus h, right? So 0 plus 240 seconds, right? Fine. So okay, they have performed the calculation over here. So at time t equals 240 seconds, we have an approximation of theta 1 as 675.65 kelvins. Now, since our target is to find the approximation at time t is equals to 480 seconds, we need to of course perform one more iteration, right? So now one more step, sorry, not iteration. So for the next step, we are taking the value of I as 1. So our T1 is of course 240. Now our T2 will of course be 250, 480, right? And we have calculated in our previous step the approximation for theta 1, right? It was 675.65 kelvins, right? Fine. So we'll again use the same set of steps to calculate the value of K1, K2, K3 and K4, the values of these four slopes at these four particular points, this point, this point, this point, and this point. You just find out the functional values at those points. You come up with the slope values as what? K1 is something like 0.044 something, K2 is minus 0.31 something, K3 is minus 0.34 something, and K4 is minus 0.25 something. Okay, yeah, after you have found out the values of these four slopes, what you'll do again, you'll do a weighted sum of them and you multiply it with h and add it to theta 1. Okay, so we know from our last step, we have found the theta 1 to be 675.65 kelvins, right? We just plug that in over here. We plug in our respective K1 values and weight values that Runge have decided after deriving them using the Simpson's 1 by 3 rule, right? These are the weights and the corresponding slope values, and they are of course together multiplied with this weighted sum is multiplied with the step size 240, right? And in our question, our value of h was given as 240 seconds, right? Now, if you perform all these mathematical calculations using a calculator, what we will end up with is a final approximation that goes something like this: 594.91 kelvins. Okay, and we have already discussed that our exact value was something like what? 647.57 kelvins, right? It was the root of this nonlinear equation here. So this again, when we are using the RK4 method, we are seeing that whatever approximation we have ended up with is kind uh, of course, it's a bit far apart from the exact value, right? But it's not as bad as the approximation that we got in the case of the RK2 method and the Euler's method, right? So let's try to this graph basically compares the distance disparity between the approximations that we have. So the exact value was this diamond marker over here, and this square marker is our approximation that we got while using the RK4 method using a step size of 240 seconds, right? And if we use a step size of 480 seconds, we also get a very unhinged approximation of minus something kelvins, right? So of course, very drastic, right? So it's very far apart from the actual value. Fine. So again, just notice that this triangle marker is not as far apart as we have seen in the case of the Euler's method and the RK2 method. Okay. So of course, by reasonable intuition, we can say that the RK4 method gives us a better approximation for specific step sizes. Okay, let's try to demonstrate that empirical fact using this table over here. So let's see what's happening. So okay, so when we use a very high step size of 480, we're getting an approximation of minus 90.278 at the time t is equals to 40 seconds. Okay, now this is bad, but not as bad as the uh, approximation that we got for the RK2 method and the Euler's method, right? It's somewhat better, but still it's very bad, right? Now let's talk about the lowest extreme, which is the step size of 30 seconds, right? So when we take 30 as our step size, so intuitively you should get what? A better approximation, right? So we have seen that as we decrease the step size, our errors get lesser and lesser, and our approximations get better and better, right? Now in case of the RK4 method, we end up with a final approximation of 647.57. Okay. Now look at the true error and the absolute relative true errors. Okay, it's something like what? 0.00086 for the true error and 0.000134 something for the absolute relative true error, right? If you compare it to the error values, the truncation error values that we got in the case of the RK2 method, it was what? Minus 0.63 something and minus 0.09 something, right? So whatever we are ending up with the final approximation for the RK4 method using the Runge's approach, it's a much better approximation than the approximation that we got using our RK2 method. Okay, using the same step size minded. So we are of course compare for ensuring fair comparison. We are using the same step size, right? Okay, so this graph over here shows us that as we increase the value of step size, we are getting lesser. We are getting what worse and worse approximations, right? For a value of uh, while taking the step sizes as low as possible, we are converging towards the actual exact value, right? So this square marker is the exact value, and these diamond shaped markers are the approximations that we get for that respective step size. Okay, so for the step size, let's say for step size 30, we get this approximation over here, very near to the actual value, right? So if you compare, so empirically we got 647.57 as our exact value, and for step size 340 for step size 30 for after using the the RK4 method with step size 30, we end up with a value that is exactly almost exactly. So we are obviously rounding it to two decimal points, right? If we don't round it to two decimal, if we round it to two decimal points, we're getting the exact value, right? If we don't round it to two decimal points, we're getting a very minuscule amount of error, right? Very minuscule amount of true error and a very minuscule value of the absolute relative true error. Okay, so if you compare it with any of the preceding algorithms that we have learned, which is concerned with solving first order differential equations, we can see that the RK4 approach is by far the best method, right? So uh, once uh, one of course commonsensical implication from this is that the more number of points that we consider while calculating the slope values k1 k2 and so on, the better approximation of the final slope that we will get while for calculating the value of y sub I plus 1, right? For that the value of the dependent variable y that we get after the I plus 1 iteration, right? Okay, fine. So now that we have seen, okay, how do we increase that accuracy? We use more points and we use lesser step sizes, right? Okay, so this is basically the gist of the comparison over here. Lesser the step size and lesser more the number of points, the better the approximation that we get. Okay, at particular discrete points for the approximations of the values of the dependent variable y at particular discrete points. Okay, so that's okay. Here's a small mini quiz for you guys. You can, of course, if you know the answer, you can write it in the comment section of the post that I will be giving of the material post that I'll be giving while uploading this uh, while uploading the resources and the recordings, right? You can answer it in the answer the question in the comment section there. Okay. So what's the question? So we have talked about the local truncation error and the global truncation error in our Euler's methods lecture, right? In our lecture 14, I think. This is lecture 15. In our lecture 14, we talked about these two types of truncation errors, right? So I want to know from you what will be the truncation error growth rates for the Runge-Kutta second order method and the Runge-Kutta fourth order method. Okay, so whatever answer you give, try to justify your answer. Okay, so don't spoil it yourself. Try to come up with the answer by yourself. Okay, don't spoil it for others. Fine. So try to answer it, and if you can answer it correctly, you'll of course get some bonus mark. Okay, it will inshallah help you to get a better grade. Fine. So that's it from this. That's it for this lecture. The second order, the fourth order method. So I basically merged two lectures as one for this specific topic because these two are very aligned with each other. Fine. So if you have any more questions regarding this topic or regarding this lecture or any part of the lecture that you did not understand, or if you did not understand any part of my handwriting, or if you found any mistakes in any of the slides, some in any of the slides of this lecture, this presentation, you can contact me. Okay, and you can contact me at any time. Fine. So if you have any questions, of course, let me know. You can ask it in the comment section, or you can contact me. Okay, fine. Okay, that's it from my side. Assalamu alaikum warahmatullahi wabarakatuh.